Welcome to the deep dive. Today we're taking on a huge stack of material. We've got technical papers, dense documentation, some really specific case studies, and we're going to boil it all down for you.
And our mission is to get our heads around one really profound idea. It's called the Universal Signal Decomposition Framework, or USDF.
Right, and this framework makes a pretty enormous claim.
It really does. It's basically saying that complexity itself, I mean, whether you're looking at a picture, a brain signal from an EEG, financial data,
Anything.
it's
Yeah.
all fundamentally hierarchical. And the key to building AI you can actually, control and understand is to build that hierarchy right into the system.
So if we can break down any signal into its basic parts, its different scales, we suddenly unlock this level of control and generalization that's frankly been a bit of a holy grail in AI.
For years.
Yeah. So the big question for our deep dive is this. How can one single architectural idea, and it's rooted in some pretty classic signal processing and even neuroscience, give us a unified way to handle everything from tiny visual details in a photo to something as massive as governmental corruption?
It's a huge scope.
It is. Okay, so let's unpack this. I think we have to start with the core theory, using the most intuitive example we have, an image.
That's the perfect place to start. And before we get into the AI architecture itself, it's worth just touching on the origins.
That classical roots.
Exactly. When you hear words like decomposition and scale, your mind probably jumps to things like wavelets or Laplacian pyramid.
Standard stuff from signal processing, yeah.
And you'd be right. USDF is definitely standing on the shoulders of those giants.
But wait, I have to ask, how is this really different? Why couldn't we just, use a wavelet transform and call it a day? We've had that for decades.
That is the crucial question.
Mm.
The difference is integrating it with the learning process itself. It's about how we train the model's internal brain, its latent space.
Oh, okay.
Wavelets decompose the input, sure. But USDF forces the AI to learn a spatialized, meaningful representation inside its own head, so to speak. And it's grounded in how your own brain actually works.
Right, the neuroscience connection. You mentioned the visual cortex.
Precisely. Your brain processes what you see hierarchically. V1, the first stop, it just sees lines, edges, local detail.
The tiny stuff.
The tiny stuff. But as that signal travels deeper to V2 and the IT cortex, the processing gets more abstract. It starts to deal with whole objects, categories, entire scenes. USDF tries to bake that same functional hierarchy right into the model structure.
And it does that using something called the trifrequency prior.
That's the one.
So let's stick with an image. Imagine a picture of, I don't know, a leopard sunbathing. We're essentially telling the AI to sort all the information about that leopard into 3 specific but overlapping frequency bands.
The first one is the low frequency band. This captures the really coarse global structure. So the scene layout, the overall composition, the pose of the leopard.
Well, what would that look like on its own?
If you reconstructed the image from only that band, it would be, well, a blurry smudge of color. You wouldn't see any fur, but you'd instantly know, okay, that's a cat-like shape coiled up, not one standing to pounce. It's the gist of the image.
Okay, so that's the big picture. Then you move up to the mid-frequency band.
And this is where the object itself takes shape. You get the boundaries, the parts. The reconstruction here would look like a clean sketch. You can see the limbs, the head, where the leopard ends and the background begins. It gives the object its identity.
And then finally, the high-frequency band.
This is for all the fine local details, the texture of the fur, the sharp edges of the whiskers, the patterns. And crucially, this information it's often sparse. It's noisy.
So if you looked at just that band,
It would just look like static, like high contrast noise. Yeah. It only becomes meaningful when you layer it on top of the lower frequencies.
the big benefit here, the reason you do all this, is the incredible control it gives you. You've genuinely separated the pose from the who, the shape from the, I guess, how it looks, the texture.
And you see this immediately in this application they call frequency swapping. It's pretty amazing.
This is the fun part.
It is. You can take the low frequency code, the pose and scene, from a photo of a tiny house cat. Then you grab the mid-frequency code, the shape from, say, a huge, bulky Great Dane, and then you borrow the high-frequency texture code from a tiger.
And you combine them all.
You combine them, and what you get is a perfectly coherent, brand-new image of a tiger-striped, Great Dane-sized animal, curled up in the exact posture of that tiny little cat.
Which proves the system isn't cheating. It really understands that pose and texture are separate concepts.
It gets it. It's not just secretly encoding texture details in the low frequency band. The separation is real.
Okay, so we've established what the bands are, but now for the tricky part. How do you stop the system from, as you said, cheating? How do you stop it from just cramming all the useful info into one band or duplicating it across all three?
That is the architectural secret sauce. It's the core innovation, and it all comes down to an extension of the variational autoencoder, the VAE.
Let's do a quick refresher on VAEs for anyone who's a bit rusty.
Sure. Think of a VAE as a really smart compression algorithm. It's trying to squeeze a huge image down onto a tiny little flash drive.
And that flash drive is the latent space.
Exactly. And the VAE has this loss function with a little variable in it called beta. And that beta weight basically controls how hard you squeeze, how much you constrain the information you can fit on that drive.
And normally in a standard VAE, that beta, that constraint, is the same for the whole flash drive.
Correct. USDF throws that out. It replaces that single global squeeze with what we can call a gradient of constraints, applied strategically across each of the frequency bands.
A gradient. So different amounts of pressure on different parts.
Precisely. And the gradient reflects a core idea. Global structure has to be really well organized, but local details can be messy and varied.
That makes a lot of sense intuitively. Like if you're building a world in a video game, the laws of physics, the global stuff, have to be super rigid.
Rock solid.
But the individual leaves on a tree, the local texture, they can flutter around randomly. You want that freedom.
Exactly. It's like an architectural zoning law. So to force that organization on the global structure, the low frequency band gets the highest beta weight. In the papers, it's often set to 1.0. This intense pressure forces that band to learn only the most essential, stripped-down information.
And you do the opposite for the high-frequency band.
You got it.
Yeah.
That band, which is all about noisy, variable textures, gets the lowest constraint, maybe a beta of 0.5. This low pressure gives it the freedom and capacity to capture all that rich, messy detail.
So the system wants to be lazy and hide structure in the high band, but the strong rules elsewhere prevent it. It's forced to specialize.
It has no choice. And the midband, which is the bridge between them, gets an in-between value, maybe 0.75.
Now, the papers really emphasize that these aren't just three separate buckets, they're overlapping. Why is that so critical? Why not just have clean cuts?
The overlaps are the communication channels. They're absolutely essential for coordination.
The conference rooms between departments.
That's a perfect analogy. If the low-frequency band figures out a shape and the high-frequency band figures out a texture, they need that little shared space, the overlap, to make sure the texture wraps around the shape correctly. It prevents, ugly seams or artifacts in the final image.
So you monitor the overlap to make sure it's doing its job, but not too much more.
Exactly. The diagnostics they use show that for a well-trained model, the importance of that overlap should settle somewhere between, say, 0.1 and 0.3. If it creeps higher, you know the bands are starting to get redundant again.
And this is where it gets really, really interesting for me. Because this whole idea, the decomposition, the gradient of constraints, it's not just a clever trick for images.
Not at all.
The core insight is that this is a universal principle. It works for any signal because pretty much all natural signals have this same kind of hierarchical structure.
It's completely modality agnostic.
Yeah.
You can just map the specific ideas from any domain onto these low, mid, and high bands.
Okay, let's take audio. Here, we're decomposing based on how fast things change over time, right? Temporal frequencies.
Right. So the slow global patterns, the low frequency that maps directly to rhythm and prosody, the overall cadence of speech, the emotional tone.
The mid-frequency would be the melody or the words themselves, the phones.
Exactly. The intermediate patterns. And then the high frequency is for those super fast, rapid details. The timbre of a voice, the sharpness of an S sound, the stuff that tells you who is speaking.
And you can do the swapping thing there too, I assume. Take the rhythm from one person and apply it to another's voice.
Absolutely. For things like advanced voice cloning, it's a game changer.
Video's even crazier because you've got two axes to worry about.
Right, you have to decompose along both spatial frequencies, the detail within a frame, and temporal frequencies, the motion across frames.
So you get these four quadrants, and that's how you can do that advanced motion transfer stuff.
Yep. Low spatial, low temporal, that's your stable background, a slow camera pan, but high spatial, high temporal, that's for things like fast-moving ripples on water, rapid texture changes.
And you can take the appearance from one video and the motion from another.
And make character A perform the exact complex motion from character B without messing up the visual identity. The control is that precise.
The generalization is just staggering. The sources mention language document topics, sentence semantics, word choice. But I want to touch on the financial application because that makes the utility so clear.
For sure. When you look at financial time series data, USDF is basically a way to separate signal from noise based on timescales.
So low frequency is the big stuff, the macro trends, decade-long economic shifts.
The fundamental market structure, yeah. Then mid-frequency is your cyclical patterns. Industry cycles, quarterly reports, things that happen over months or a few years.
And high frequency is just the noise, the tick-level fluctuations, high-frequency trading artifacts.
Right. And for you as an analyst, the value is knowing where to look. If your low-frequency band is starting to dip, that's a structural problem, a big one. If your high frequency is spiking, that's just some localized volatility you need to manage. It turns a messy chart into specific, actionable insights.
This universality lets us apply the framework in some really critical, high-stakes situations.
Which brings us to Project Encephalon. This was a really deep technical dive in the source material. The goal was to build an unbreakable neurobiometric system.
Using your thoughts as a password.
Essentially, yes. They call them pass thoughts. And the whole thing works because USDF can clean up and structure raw EEG signals from the brain.
So the input signal is your brain activity. The first layer of the system is just decomposing that signal into biologically meaningful frequency bands.
And that mapping is key. Low frequency is delta and theta waves, 1 to 8 hertz. That's tied to your deep cognitive state, memory. The mid-frequency is alpha and beta waves, 830 hertz. That's your active conscious mind attention, motor planning.
And high frequency would be the very rapid gamma waves over 30 hertz, which are linked to intense perception, binding ideas together.
Now here's the twist, the really counterintuitive part we have to unpack. They use inverted beta weights.
Inverted. So they flip the whole constraint system we just talked about for images.
They flip it completely. In our image example, we squeeze the low frequency band really hard because that's where the core structure was.
Right. So here, they're putting the lowest constraint on the most important information, the delta theta waves linked to memory. That feels backward.
It feels completely wrong until you think about the neurology. In your brain, those slow, low-frequency oscillations, delta and theta, they carry the stable, critical patterns of your past thought. They are the cognitive fingerprint.
Ah, I see. So you don't want to squeeze them. You want to preserve them perfectly.
You need to preserve every single nuance. So they set the low-frequency beta incredibly weak, just 0.1. You regularize it as little as possible.
Okay, that makes sense now. And the high-frequency gamma signals, the fast stuff, that's actually the noisiest part of an EEG.
Exactly. Gamma is super sensitive to muscle twitches. It's transient. It's noisy. In a security system, you want to clean that up. You want to regularize it heavily to get rid of the noise and just keep the sharp, essential perception data.
So it gets the strongest constraint.
The strongest. A beta of 2.0. This domain-specific inversion is what makes the whole system work.
And that solid foundation, that tailored decomposition, is what enables all the advanced security features. This isn't just a simple password.
Not even close. The other layers, L1 to L4, are all built on top of this frequency structure. Like liveness detection, making sure it's a real thinking brain, is 99.8% accurate.
Wow.
It looks at the micro variations in that high-frequency gamma band. A real brain produces incredibly complex gamma that a simple recording just can't fake.
What about faking it with a generator, a synthetic signal?
They have a layer for that too. Synthetic signal detection is 97.3% accurate because it uses cross-band power ratio analysis. Artificial signals tend to look too clean, you know?
The transitions between bands are too perfect.
Exactly. A real brain signal is messy. The decomposition makes that artificial cleanliness stick out like a sore thumb.
It's incredible. They even have duress detection at over 92% accuracy, probably by looking for weird changes in those stable, low-frequency bands.
The whole system is just enabled by that initial structure. And the performance is, well, it's clinical grade, a 99.7% true acceptance rate, and it's fast, just 7.2 milliseconds to authenticate. It's proof that building the signal's native structure into the AI pays off big time.
To bring this all back to a global scale, let's look at that other high-stakes problem, detecting governmental corruption, which, like brain signals, operates on many different scales at once.
It's a perfect analogy. You could feed a massive, messy pool of data financial records, procurement documents, policy changes into a USDF system, and it acts like a semantic filter. It sorts the anomalies into categories that map directly to the frequency bands.
So you're turning data points into actual investigative leads.
Precisely. The low-frequency anomalies are the big, slow-moving systemic problems. Institutional capture, regulatory bias, Stuff that happens over years or even
The
decades.
slow drift in budget allocation that doesn't make sense.
Right. It's the kind of thing that requires a policy response, not just an audit. Then you have your mid-frequency anomalies. This is the procedural stuff. Bid rigging, vendor favoritism, patterns that repeat over months or a couple of years.
The organizational level of corruption.
And finally, your high-frequency anomalies. These are the individual transactions, kickbacks, invoice fraud, things that happen fast over days or weeks.
Like a bunch of payments that are all just under the approval threshold.
The classic move. And the value for an investigator is that this is immediately interpretable. If the AI flags a low-band anomaly, you know you have a systemic issue to tackle. If it flags a high-frequency spike, you send an audit team to look at a specific batch of invoices.
It doesn't just say something is wrong, it tells you what kind of wrong it is and what kind of response you need.
It transforms a giant, scary pile of suspicious activity into a neat, prioritized to-do list.
So to pull it all together, USDF takes this natural multi-scale structure that's inherent in basically all complex signals, and it builds that structure directly into the AI model's internal world,
Through that targeted gradient of constraints we talked about.
which results in systems that are way more powerful, much more controllable, like we saw with the image swapping, but also just fundamentally more generalizable.
It really does unify these decades-old principles from wavelet theory, what we know about the brain, and modern information theory all under one roof.
Which leaves us with a really important final thought for you to chew on. If this framework can learn the core hierarchical structure of signals from fields as different as neuroscience and finance and climate science, does that enable a kind of true cross-domain synthesis?
That's the billion-dollar question.
Could the abstract principles of organization that a model learns from, say, analyzing neural network patterns, could those principles be transferred to help us understand other incredibly complex systems, like gene regulatory networks, or even the dynamics of an entire economy? That is the profound and I think really far-reaching promise of universal signal decomposition.